the last example of lesson 15, differentiating exponential functions. Now, in this one here, we've learnt that the differentiation of an exponential function is e to the x. We've also learnt the general rule, the chain rule, so if we want to differentiate when an exponential has a more complicated power, we just simply bring the gradient function down as a coefficient. So in this video, we've got this curve here and we have this function, y is equal to e to the x on x. Now, use calculus to prove that the local minimum shows in the only stationary point is the only stationary point in the curve and determine its exact location. Okay, so local minimum, so we're thinking this is a dy by dx is equal to 0 situation if it's after a stationary point. Only stationary point, so we're expecting when we solve for this there's only one solution. That's what we're hoping here, and then we're going to prove its exact location, so we're not going to do any decimal places basically. And it looks like they've given us a curve here. Thank you very much for doing that, and we're meant to find that point. So first thing, we got to differentiate. Y is equal to e to the x on x. Let's change that to y is equal to e to the x times by x to the negative 1. Now we can use the quotient rule here, but I prefer the product rule. Let's write u under here and v under here. We want to differentiate this. U dash becomes e to the x times by x to the negative 1. So remember, that's our first step, u dash and v. And then we add on, and then we're going to go v dash times by u. So v dash is going to become, well, you bring the negative 1 down, x, the negative 2, times by u, which is just e to the x. Absolutely love differentiating the old exponential function. Next line, let's see if we can clean this up. And then we've got take on x squared. And then we want to find a stationary point. So I'm going to make that equal 0. Now remember our little trick for solving these. If I times by x squared, I can see I can get rid of my x squared in the denominator. What does this now become? I've got 0 is equal to x e to the x take e to the x. Okay, so we can see how we've used that little trick to get rid of those pesky denominators. Next thing is I can see I can factorize by taking out a factor of e to the x. So now I can use my null factor law. So null factor law, I either want to make this one equal 0 or this one equal 0. Okay, so let's write that out. I've got e to the x is equal to 0, and I have x take 1 is equal to 0. I can see x is one solution. And is the exponential function ever equal to 0? Where you may be wondering, what does that look like again? Well, you know it looks like something like this, and you know there's an asymptote here. Y is equal to 0. Therefore, there is no solution. It approaches 0 but never gets there. When negative infinity approaches 0 but never quite gets there. So there we go. We've got x is equal to 1. Okay, so we've done a good job there. Now this we hope is the minimum. We can double check that, but we can see from the graph that it must obviously be the minimum. And now we need to find the coordinate. So what we can do is we can go, this is 1 comma something. So let's sub 1 into our original y function, which is here. Okay, so y is equal to e to the x on x. Let's sub in 1. Y is equal to e to the 1 on 1. And therefore we have now our coordinate 1 comma e to the 1. Okay, and then we have it. We've just shown that there's only one stationary point, and it's a minimum through looking at the graph. You could use the double diff test to make sure it is a minimum. And yeah, we did that using a bit of product rule and null factor law. There's so much stuff coming together here. Okay, I hope you found this video useful. As always, if you want to practice more questions, which I really recommend, you've got to go to Sadler Unit 3, Exercise 6B. Thank you very much for your time.